Okay, good morning. So before the class, because we got in Piazza, we got a few people asking about the questions. Okay, the first question is about the survey report and the proposal you already handed in. Mainly, we said this one, of course, TA will put a mark, say how good they think the proposal is, but they will not give a grade. There's no score attached to it. Mainly is TA want to give you feedback to say whether it's a good project, whether your references, you submitted, those references are good references. Mainly TA wants to provide some help. Remember, this is just a proposal. Why we want you to hand in at the end of the fourth week? Mainly, we want you to start early. So once you go through more and more course materials, if you have refinement or even you have some changes, usually discuss with TA with me, it is quite possible. That means what you proposed may or may not be very finalized. But at least at this stage, you form a nice group, you start early. It's much better you do it after the midterm, okay? Because this course project got 35% of your total grade, which weights more than any single midterm exam. Actually, it almost weights the same as 2 midterm exams. Okay, to that extent, it's very important. And we also want to grade not only by TA, but by the whole class. That's why I really want you to spend a lot of time thinking and working on it. Forming a team itself is good because usually 2 heads are better than 1. Okay, you got discussions, you got brainstorming, you probably can go deeper. You really can create something. Okay, so we strongly encourage you to form like 2 or even 3 people form a group. That may help each other to go deeper. Okay. Then another thing is about a midterm exam. Okay. Some students ask about a midterm exam. One student actually clicked this button, said it was not linked. Okay. I realized this. I put the new one. I actually linked it. There's no password control. So you just click it. You find the previous midterm exam. I did put the first midterm exam of 2013, which is 3 years ago. I don't want to put last year's. Simply says, you probably, the reason I want to put 2013 is there are some content differences. That means 2013 we covered something different from what we cover now. Then you look at it, of course there are something similar, but there are lots of contents we cover in 2013 we do not cover here. And we have many new materials. I don't want to, show you for the new material what should be the questions. So you can go down, you look at the exam. That's the style. It simply says, I almost leave 1 page for you to work on 1 sub-question. Total, I think, is somewhat like 9 or 10 pages. Simply, you don't want to write too much, but I give you enough room. You can write more if you want. Remember, the midterm exam is always very tight, so even I give you that much space, you don't want to fill it up. Okay, you just write the key points, then you move on to the second question. So, any questions about this? Remember, I do allow you to bring 1 sheet, means 2 pages. Okay, 1 sheet, that means double-sided printing, cheat sheet. You can write whatever you like. That's the only help. Okay, there's no iPhones or no other things allowed. Okay? Of course, some people may ask whether the computer, the calculator is allowed. I do allow you. I do not think that you will need a calculator, but feel free. If you want to bring a calculator, it's okay. Okay. Any other questions related to the midterm? Yes? Yes, the question is whether the cheat sheet double-sided can be typed. I actually encourage you to type it because you can print smaller. If you write it, you probably cannot write that much. So you can print any font you like. I said the magnifying glass is allowed. Okay, so you can print only font size 3 or 4. It's fine. I don't care that. Okay. Yes. You can look at this. Essentially, it's very similar. How many questions? I usually give something like 9 to 10. Okay. Usually, I think we have 90 minutes. So-called 90 minutes is I actually start a little earlier. Okay. We probably can discuss whether we start at exactly 9:30 or 9:20. But I give you 90 minutes. We have to finish in 90 minutes. 90 minutes, if I give 10 questions, means 9 minutes a question. Okay, so that's a number of questions I expect. Usually 9 to 10 questions. Okay, other questions? It's very similar to the style. You can read the sample program, the sample exam. Okay, but the contents, of course, will be somewhat different. I think based on my previous experience, the exam, the score, average score in the class is pretty high. Okay, simply says you want to have a thorough review, not to think about I just get 80 points, I will be number 1 in the class. 80 points, you could be the last one in the class. Okay, so that's why you still need a good preparation. Okay, I think. Last year, the midterm exam was somewhat close to 90 on the average. Okay, so it simply says the student actually did pretty well. Hopefully, you carefully look at it. You need a thorough preparation because I don't want you to think you just missed one question or two. You drop at the end of the class, at the bottom. You may complain, but the whole class is very competitive. Okay, this is a grade level class. Okay, so hopefully you know that you can look at it, which may help your review. Okay. The exam time is exactly fixed. You can see the exam time is March 1st, Tuesday. Okay, just mark it. Don't miss that exam. Okay. I actually changed the order of the slides a little because last time we did change the order of the presentation. I brought the past sim that similarity search earlier. I put the classification down. Okay, so then some changes of the slides. Okay. So let's just review a little. Actually, we pick up Christos Falouza's example. Actually, this morning I just got his email. Of course, not discussing this, discussing other things. And this is about similarity search, who is most similar to Christos. Okay. We mentioned we actually tried a few popular used similarity measures. One is based on random walk. Especially, we call this one the personalized page rank. Okay. The general philosophy is similar to PageRank. If you think of the PageRank, you got an in-link. If you go where you want to go, if you do random walk, those nodes which are highly linked, okay, very likely your random walk will reach there. That probability actually is pretty high. Then, if you want to say who is most similar to you in Facebook. Okay, you may actually go, if you use PageRank, you say who is ranked high. Likely you will grab those very highly visible nodes. But, if you yourself are not so highly visible, you do not fear they give you a good answer because, Obama is very highly visible, but you are not very similar to Obama anyway. So that's the reason if you try to use random walk to do PageRank, it's good. Okay, but to do similarity search may not be so good. Okay, it's different semantics, right? And there's another one called SimRank. sim rank, just by name, you already think this is really for similarity. Why? Because sim means something like similarity. Okay. Sim rank was proposed by Jennifer Widom. Actually, both of them were proposed by Jennifer Widom. I also mentioned on Thursday, Jennifer Widom is going to give us a talk on, I think it's on the second floor, 2405, 4 to 5 p.m. Thursday. I just say, if you like to go, you should go earlier because likely, okay, probably 10 minutes before there will be no seat available, because I think the whole, not only whole computer science department, many other departments, they may want to get in. Okay. And this sim rank, the basic idea is if you look at the in-link, okay, just thinking about in-link, who is similar to this node, Z, then you will say, actually you want to see the similarity based on who are your neighbors, whether those neighbors are very similar. Okay. How to define the neighbors are very similar? If the neighbor is just the same. Okay, they collide just the same. You yourself is most similar to yourself. If these two neighbors are colliding, that's the same, then they are very similar. Okay, but in many cases, you do not know your neighbor similarity. You have to check a neighbor's neighbor similarity because the neighbor similarity defined the same way as you do. Okay, so we can look at the detailed formula. Okay, this is a detailed formula. Sim rank actually was defined by it's based on the object is maximally similar to themselves. That simply says, if you just say who is most similar, the most similar one is to yourself. So if this A equals B, the similarity is 1. A is not equal to B, you can say similarity is 0. But when A is not equal to B, you actually are trying to use this formula to check their neighbors. That means you look at similarity, A and B, say who are most similar. You will say this I is in-link neighbor. Okay, just think of neighbors if you do not care that much about in and out. So you say A's neighbor, B's neighbor. You look at their neighbor's similarity. You can see this is the similarity of A's neighbor and B's neighbor. Okay. Check every pair of neighbor, their similarity. That's why you use I and J. Okay. The first thing is you can imagine this is expensive. Why? Because you think about, suppose I have 10 neighbors, you have 20 neighbors. How many neighbor pairs you will get? You get 10 times 20, right? You get 200 neighbors, pairs. But that's not it, okay? Because you check their neighbors. How do you check them? You check their neighbors' neighbors, right? You think about this. That immediately get into quadratic algorithm. Just check new neighbors. You involve the whole network in a quadratic way, okay? So that's very expensive. That's why actually our TA just use our DBLP data sets, a portion of it, just on data, machine learning, like a database, web, those conferences. He put down into his laptop and run it using SimRank. The first iteration, he could not finish because the graph is so big. And you get a quadratic, check neighbors and neighbors' neighbors. You just cannot, it just involves too much computation. Okay. So finally, I changed my homework. I will not ask you even to run on that small data sets. It's not too small, okay? It's just about probably 100,000, okay? But you just cannot finish. But also the similarity, the real semantics may not be very good. That's the one I actually just show the example, okay? But anyway, this one, both SimRank and personalized PageRank, these two algorithms are very, very popular. And actually, people are using it in many, many different ways. Okay. Of course, we said we want to find a peer similarity. That means in a Facebook, you want to see who is most similar to you, okay, rather than you just want to find Obama. Okay. In that sense, these two similarities may not give you very, very good semantics or examples. Because This one actually just try to check neighbors and neighbors. If you just look at semantically, not necessary, you actually just check your neighbor is the best way. Another thing is these two are both defined in homogeneous networks. Okay. That means you really define a web page or Facebook, just look at the person. There's no any other information. But we want to search similarity using heterogeneous network. For example, the publication. Not just based on the co-authors. The similarity is based on what papers you write, what terms you're using, what venues you're publishing. Okay. Of course, including part of the co-authors as well, or including even could be citations, right? But we just, this personalized page rank this score is defined. It's very similar to PageRank if you look at the original PageRank score. The difference is this B is a stochastic vector, okay? Or people call personalized vector. You can use this, you can adjust it. And in the programming assignment, TA already give you suggested parameters, okay? You just follow his suggested parameter because if you use all different parameters, he may not know how to grade it because everybody using different parameters generates something different. Okay. Some students already run this personalized PageRank on the DBRP data set and even send me emails said that the result looks a little odd. Said you got two very different people get a personalized PageRank, say who are most similar. They seem to be similar to the similar set. That looks very odd. Actually, it's not odd. We actually show it because the personalized PageRank carries some philosophy of PageRank. So those people who are very, very visible, like publish many, many papers, likely you will point to them rather than you point to your real peers. Okay. So let's look at this simple example. Okay. Last time I briefly introduced you, but I want to emphasize a little more. You see how it is computed. Okay. First thing is I just show you this table. This table is a very, very tiny table, just containing 4 conferences and 5 authors. Okay. But we put a mic, we put as colored, simply say we want to take a mic as a reference, say who is most similar to a mic. Okay. Then we have Jim, Mary, Bob, and Ann. And Mike published only 3 papers, 2 in Sigmod, 1 in VRDB. Okay, those are database conferences, but I don't care which conference, just 2 conferences. Okay. Then Jim published 50 versus 20. Okay. Then you get, like Bob published 2 and 1. So by common sense, you look at it, you say, oh, the most similar one must be Bob, because they published the same number of papers in the same venue. So they must be very similar. Okay. But if you carefully code personalized PageRank, SIMRank, random walk, and pairwise random walk, okay, these 4 measures, you code them, you actually will find who is most similar to Mike. If you look at these 4 actually all vote for Jim. Okay. You'll probably say this is a very surprise because Jim got 50 papers and 20 papers. Why Jim is most similar? That's exactly the graph if you use PageRank or these kind of algorithms. Okay. Those containing more, visibility, more links, they will extract. If you try to propagate your random walk or pairwise random walk, you propagate, then you think your propagation is random, but the link is not random. Okay, the link which has most links, they will absorb your random walk. Whatever you will go down to them. Right? So that's the reason you can see, because Jim got so many papers, it's like a tractor. Okay? He has more links to those conferences. So then Jim basically attracts most of the random walk values from Mike. That's why they got a ridiculous answer, say Jim is most similar to Mike. Okay. But why these PASSIM can overcome this problem? Okay. You look at how the PASSIM was defined. Okay. That's the one, Yi Zhou San, she defined this. Actually, this one has been very popular. I said it, she just graduated 2 years ago. Now her paper already, like this paper, already cited more than 200 times. That means other 200 researchers got papers following her work. Okay, so you look at this. What is the definition? She got magic. She can control this. Okay, actually, this P is your pass, your guided pass. For example, the P you said APCPA. A is author, P is paper, C actually is a conference. Of course, we can say venue. You can say APVPA. This is the P, this is the A. This simply says, if you say these two are most similar, how you do it? You first go up to the paper, because you author this paper published in this venue. And the other guy said, I also author another paper published in that venue. So if we want to think about a venue-based similarity, we'll go to APCPA. Okay, so you follow this path. Okay, then if you want to see two authors, X and Y, how similar they are. Okay, her definition basically this. Okay, if you go from X to Y, actually, of course, the same thing. You go from Y to X. Okay, because this is symmetric, right? You publish paper, you link to this paper linked back to you. It's the same thing. So it's undirected. Okay. But you can think in a way, if you take one author goes to the other, okay, from X to it goes to Y. Okay. How many paths? You must follow this path P. How many paths you go from X, you can go to Y. Okay. Then what is the denominator? Denominator, actually, you flip this two back. You can say this is the average of these, sum of these two, right? This one is you go from X, follow the path, go back to yourself. This says Y, you follow the path, go back to yourself. Okay. Then you think about Jim, Mary, Jim, Mike, and Bob. You think about this. What will happen? Okay. Suppose you are very popular authors. Suppose you are very productive one. You got 50 papers in Sigma, 20 papers in VRDB. Suppose I also got this. Okay, so why we two are very similar? You can think about this. In the graph, you want to go to me. Okay, but because you publish 50 papers, I publish 50 papers. We both in Sigma. We have lots of paths to go back each other. Right? So you can see this is very big because you have so many, right? You can go back. And here you can see this, because I publish 50 papers, I also can go from me, go to Sigma, to go back to me, right? I also have many paths go back to me because, I publish Sigma, and I can go from one paper to the other, right? So the same thing as the other one, okay, like Jim, okay. So you can see our similarity is very high because we both got many papers. What about one guy got many papers, one got very little paper? Okay, then you see what happens. If this guy is Mike, this guy is Jim, okay, what will happen? You can see Mike does not have that many papers, right? Jim has many papers. So Mike can go to Jim in a moderate way, right? It's not that many you can go to Jim, okay? But Jim can go back to Jim in a very, very sophisticated way because there are so many papers he can go back and forth, right? So denominator becomes bigger. The numerator becomes small, so you're not so similar, right? What about Mike and Bob? Okay, you can see Mike and Bob, they both publish a small number of papers. They go down in a small way. But if you check a denominator, they are also in a small way. So finally, Smaller divided by smaller, it becomes closer to 1. Is that clear? Okay? So you can see that's her thinking, the definition, her design. And it works nicely. Okay? Sometimes you don't need a rocket science to make it work. I remember Jim Gray got Turing Award, and then some journalists visited him, that's many years ago, and asked him, so what is the invention people give you this big award, like a Nobel Prize? He said, if you and your brother go down to the bank, you withdraw the money at the same time, you don't want in the 2 different ATM machines, you don't want to scramble. You want the money finally give you, it's the right amount of money. Okay. The journalist said, this is not like a rocket science. How could you get Turing Award because of this? Actually, there are lots of theory behind it. Plus, he was the first one who invented the whole relational database system. Okay, lead the IBM team. But remember, a lot of creation, big creation, if you go back down to the earth, it may not be that sophisticated. But you can be a big inventor if you really catch the essence, right? So let's look at the real example, okay? I pick up Anhai because many people, know him when if you were earlier graduate students, okay? Because he was a professor here, assistant professor. And after a few years, he was grabbed by University of Wisconsin. Now he's a professor in Wisconsin. We pick him because he's not as big as Jim Gray or Mike Stonebreaker. Everybody knows him. Okay. We pick him as who is most similar to Anhai Duan. Okay. The interesting thing is if you run personalized PageRank, that's exactly some student communicate with me, said they run some no-namer, finally get some big name and most similar. You probably can see Anhai Duan, of course, is most similar to him. But then if you look at the remaining people, actually those are all very big names in the field. For example, Philip Yu got probably most papers in DBRP, in whole computer science. You got like 800 papers or 900 papers published. And Hector Garcia Molina actually is both Kevin Chiang and Aditya's advisor. He was department head of Stanford. Is a lead in the whole database field. Gerhard Weikom is a major lead in Europe on the web and the database. So he basically, if you look at this, you probably say how Anhai Duan could be so big name, right? So get all the big name people down there. But if you look at SIMRank, you look at those names, probably you almost know nobody, because SIMRank tends to be to just check neighbor and neighbors in a way to be very specific. It's so specific. Finally, all the other specific people also have this share similar kind of weights, but not even in the same field. Okay, so that's a reason you may not know the people. Then the interesting thing is that you look at the past SIM in the database, what they will get. Okay, Yizhou actually reported. Actually we took Anhai Duan and asked you to do homework. The data may be slightly different. You may find slightly different set of people, but it's very interesting. You will find the Jignesh pattern for sure. Okay, and when I actually present this one in University of Michigan, Ann Arbor, they were all laughing. Why? Because Jignesh Patter was a professor, assistant professor in Ann Arbor, okay, teaching database as well, doing research. But almost same year was grabbed by Wisconsin. Okay, now they two are in the same group. Okay, actually next month in April I will go down there. Because that's a database 40 years anniversary. I graduated from Wisconsin, so they ask everybody to go back. Actually, the Wisconsin database group really generated a lot of very known people, because UC Berkeley got 2 professors in database, both graduated from Wisconsin, And then UIC, then like a Cornell has Johannes, those are all the big universities. Actually, the other one, like Renee Miller, also graduated from Wisconsin, and she is a professor at University of Toronto. But interestingly, if you see Jignesh Patel, there are 700,000 authors, okay, in DBRP. And this program actually just picked up Jignesh Patel. You probably can see these two. They are in the same area. They are in the same research group. And they got a PhD not too far away. Okay. So that's definitely very similar. And how they figure out is just based on the publication venues, right? They publish in the similar venues with a similar number of papers, you probably can see. So this actually is very interesting. If you look at this, it's very telling. The similarity you got is really, really good. Okay. It's very simple formula, right? You'll already see that. She actually used this formula, go down to Flickr, pick up a flower, like this flower. This is a lotus flower. Say, which picture is most similar to this one? Of course, you can use image processing, but image processing will not give you a very good result because the image processing look at the picture similarity. This one could be green, the other one could be blue, or something. You will not be able to even recognize they are very similar, right? But the interesting thing is, for Flickr, you have tags. Not only you have tags, but also you have users, you have group tags. Okay. For every image, you have these three heterogeneous, data set linked to it. Okay. Then, if you want to look at similarity, you can use, for example, you can use a simple path like image tag image. But actually, if you use image tag image group image tag image, that means instead of just thinking about tag similarity, you are more thinking about a group similarity. You actually get a better result. You can see. If you look at this one is just based on tag similarity. Tag similarity, of course, everybody will say, this is a flower. Okay, the flower is similar. And they may say other things. Okay, but you probably can see, of course, this lotus flower is most similar to itself. But if you look at the others, none of them are really lotus flower. Okay, like this bird, definitely not even flower. Okay, so, but people actually tag in a many sophisticated way. So your similarity will get confused. But if you look at a group similarity, okay, that means you not only look at the tag, but also you look at a group. You actually get a very good similarity. You can look at those flowers. They are all like a lotus flower in different ways. Like this one has no real color, but it's still a lotus flower. I mean, the pond has a lotus flower, right? So you probably can see this is a pretty good similarity. That implies actually you need to find the right path to get a good similarity, good semantics path. Okay. So both similarity measure and path measure are very useful. Okay. Then she actually tried many other interesting examples. One example is like you have PageRank, you have PathSim. We all use the same CP, ACP. This is the C is conference, A is author. You try to compare two conferences based on their author set. Okay. If you use a personalized PageRank, remember who got more papers, who are more known. Actually, you are going to point to who. So then we pick up not so known conference, DASFA. I don't know how many people know this conference. It is a Pacific Asia database conference. Okay. It's a little regional, and it is not like a competitive to Sigma or VRDB, those conferences. But if you pick up DASFA, you actually will find that these conferences like ICD, VRDB, Sigma, those are the top conferences. They say these are very similar. Obviously, they are not at the same level. Okay. But the interesting thing is if you use PathSim, you probably can see that's a very similar. DASFA is very similar to DEXA, WIME, AP Web, those conferences. The interesting thing is those conferences, DAXA actually is a European database conference, but second tier. Okay? So those second tier conference, they are very similar. They share many authors, actually, because they could not get into the first tier, right? And if you look at another one, suppose we still use AP-CPA, but we use SIMRank. But SIMRank will give you something very focused, but it actually is not that similar. You probably can see those are the conferences. Many you may not even know the name. So that simply says the SIMRank also may not be as good as like a Sigmod, like this one you can see. They all get into the top conferences similar to Sigma. Okay. Then another interesting thing you may think about is you get this pass, CPAPC, that's a conference to author. What about I make this pass duplicated, like make this pass once, twice, 3 times, many, many times. Okay. She actually tried this to see how the semantics may change. The interesting thing is you make pass twice. Of course, the computation-wise is much more expensive. But the semantics actually is pretty good. You look at this, you probably, if you are in the database field, you probably feel these are very good ones because Sigma is very similar to VRDB, ICD, TKD, Sigma record. Like these are very good ones because remember, once you turn this one, not only use the pass once, but you use it twice. Okay. To some extent, you bring the Sigma, the VRDB, those conferences, originally they are different conferences, but because they share authors, you turn them around one more time. These similar conferences, somehow they have more edge. If you think of matrix, they are not empty anymore. They have more connections. To that extent, you actually will enhance the semantics. Okay? But that's not an efficient way to enhance it. Okay? Later, we are going to learn those semantics on the embedding. Like you use the nearby keywords or something, you nearby information, you embed it. It's much more efficient than this way to do it. Okay? But if you try to turn this one many, many times, actually you will get something very strange, like this one. This one, we say infinite times. So of course, we can never run infinite time. You just run many times, right? Like 50 or so. You got a Sigma is most similar to triple AI, like ESA, stack, POC, PODC. This is the principle of distributed computing. NIPS is neural information network. These are all highly regarded venues. But once you turn it around many times, actually the semantics on their own differences will disappear. Okay? So you probably can see, once you turn on many times, the semantics becomes just some known conferences instead of the really similar. They do not really share that many similar authors anymore, okay, because the chain goes too high. Okay? So simply says the advice is you only use it once or twice. Actually, use once is good enough. Okay. If you want to really find the semantics links, you use other methods. Okay. Why we also suggest you use a smaller number of times? Because the computation is very expensive. Okay. Why the computation is very expensive? You can think about this. Okay. Just to say we have APVPA, okay, author to paper to venue to paper to author. That chain involves several matrix multiplication, right? So author to paper, you can think is one matrix. Paper to venue is another matrix. Venue to paper is another matrix. You need 4 matrices multiplying together to give this chain. The matrix multiplication is pretty expensive, right? So in that context, if you want to give a query, you click a button, you want to get the results out, you cannot do on the spot the big matrix multiplication. Okay? Even this one is cheaper than, say, SIMRank, okay? But still quite expensive. How to reduce the computational complexity? Okay. So Izhou actually worked out an algorithm called co-clustering algorithm to do it. What do we mean the co-clustering? Co-clustering means you don't need to compute everything on all these matrices, but you compute only the promising ones, okay? Only the part which can be clustered together. Okay? You just think about this, okay? If you really play the whole DBRP data you program now, the DBRP got more than 2 million papers. How many venues they have? They have tens of thousands of venues. How many authors they have? They have close to 1 million. They have 700,000 to 800,000 authors. Okay. And remember, not all the authors will author all the papers. Not all the authors will publish all the venues. Actually, things are very focused. If you think about this, if you were working in data field, you probably say, I will publish in Sigma or publish in KDD, but I will not go to computer graphics or robotics or computer theory, publish papers. So the real link is very narrow. If you can cluster those links, do all the computation, you will get all the things you need, instead of you try to compute it with the whole full spectrum of all the venues, all the papers, right? So that idea, she actually first compute the matrix based on the feature objects and target objects, and only compute the portion which are, that means you first do some kind of clustering in both ways. One way is author, one way is venue. You cluster them, you only compute the cluster part. Okay? The other part is too sparse. You compute it, just waste your time. Okay? So that's the way she computes this top K threshold. That means she does not say I will not miss any single one, but only compute the top ones. That means the most things they have values, the top parts. Okay? And if you set up a top K threshold, you guarantee within this top K, you want to find top K most similar, you will get the right answer. Okay? But there's no point you want. For example, you remember you say, who is most similar to me? There are 700,000 authors. I don't want to linearly rank them. I only rank, you say most similar, I want to find top 50 most similar to me. That's probably good enough. Right? I don't want to find who is ranked as 500,000 there and 500,000 know what. Okay, that doesn't make sense. So to that extent, you only need to compute top K. Right? So this work actually got lots of impact. Lots of people following this. This paper just published in 2011. And last several years, even in KDD or Sigma conference, you just look at the title. The metapath comes not pretty frequent. It's quite a bunch. They just follow her convention, her philosophy. Okay? They use metapath-based similarity, okay, doing computation. Now you go down to even this year's KDD submission, you search metapath, you will find quite a few papers, submissions. Basically, she first proposed this. Actually, even the reviewers say whether this is a good term, whether it should be metapath or some other path. But finally, she insists to use this term, and then it becomes a standard already. Okay. And there are many following work. I probably should introduce you one interesting one, is this one. Okay. This metapath-based learning, this one called user-guided metapath selection. She published this paper in the KDD 2012 and got the best student paper award. Okay. So we will get this. This picture is, anybody know this one? Actually, if you have a sharp eyesight, you probably can read it. This one actually is the Nobel Peace Center. And remember, I show you one called Stockholm, their city hall. That's a Nobel Prize for science, medicine, physics, and all the other things. But for peace, it is in Oslo. And they have this peace center, get all the Nobel Peace awardees down there. Actually, The peace award is a very special award because it really impacted the whole world quite a lot. I think at least now there were 2 peace awardees. One is Mandela, one is Aung San Suu Kyi. Those one, they were in prison for many years, and they serve as a head of the state, right? One in South Africa, one is in Burma. The Burma one just elected, I think, a few months ago. And now we look at this work. I actually changed, if you look at the previous slides, if you printed, you would think I changed quite a lot. Actually, I only changed the order. Okay. I will put this user-guided metapath-based clustering in heterogeneous network as the next one. Then the original classification, I put it down. Okay. So let's look at the metapaths. We already know if you try to find similarity search, you need to give a metapath to carry right semantics. Okay. Then the people may immediately ask, saying, you need the user to give you metapaths. What about the user does not even know? User does not even know your structure, your path. Then how could they give you metapaths? Okay. So plus whether one metapath is enough, or you need a multiple metapaths combined in some way to carry the right semantics. This is a very good question. Okay. The question, of course, after Izhou finished that paper, the paper published in 2011, in 2012, she continued work on this metapath, and she worked out a new way called user-guided metapaths. Okay. What is user-guided metapaths? Simply says, what about a user does not know? Okay. Which is very valid. Okay. User does not know how your network is structured. Okay. But the user can give you examples. User can say, oh, Obama is very similar to Hillary. Okay. For what sense? They don't tell you, but they just say this. You probably try to find out why. What is the metapath to make these two very similar, right? Or they may say, oh, actually Obama is very similar to Putin. Then very likely the metapath will be completely different, right? So you can see the people have different thinking on similarity, right? So then she just gives this example to show you, actually, if you give me example, I probably can work out a good metapath for you. This one just to show you, there are a bunch of authors, okay? Like a total, suppose there's 8 authors. Okay. You want to give similarity, you want to find the clusters, okay? But one way you think about is they can give you similarity in the way you can see these 4 authors is from UIUC. Okay. These 4 authors are from Microsoft Research. Okay. If people want to focus on the similarity more on the organizations, okay, that means where you come from, okay, they can pick up, say, 1 and 2 are very similar, and 7 and 8 are very similar. Likely you may say, oh, that similarity means they come from the same institution, okay? But you look at this. They say these are the 2 venues they publish papers, okay? This is KDD conference, this SIGMOD conference, okay? If they are thinking these authors, if they are grouped or clustered or in a similar way, is on the venues. If they publish substantially in SIGMOD, they are similar. Or they're substantially in KDD, they are similar. Okay. In that way, they probably can give you examples, say 1 and 7 are very similar, 2 and 8 are very similar. Okay. If they say that, you probably say, oh, that means actually the similarity is more on the venues. Okay. It's more like this. You can say Newton and Einstein are very similar because they are all working on physics. But you may give another one, like you can say McCarthy and Mike Stonebreaker are very similar. Maybe they are all good researchers who got a Turing Award or something, right? So you can give a different way than they may see underneath, what are the paths? What are the weight of paths? The more interesting thing could be this. They may even say, I group 1, 3 are similar, and I can even group in that way. You can see this 1, 2, 3, 4 are similar, but I can group in the way is 1, 3, 5, 7 are very similar. Or I can group in a way, in some other way, I can make it, the similarity is affected by both. That means I would think 1, 3 are very similar because they both from UIEC, they both publish in KDD. Okay. And 5, 7 very similar because they both come from MSR, they both publish in KDD. So there you can see you will get 4 clusters. Okay. So the problem becomes, if I only give you examples, okay, can you work out a similarity measure which give me the right path? The next time you give me other things, I can do it in a similar way. I can give you the good semantics you like. Okay. So that's her idea, her motivation. That means user give us seeds. User know what are the clusters or what are similarity. They give the seed. They say 1 and 5 are 2 clusters, or 1, 2, 5, 6 are 2 clusters, 4 clusters. Then they are going to give the right clustering, finding the right metapaths and their combinations, and give the right clustering. Okay. So that's her philosophy. That means user does not need to bother underneath. You only give me some examples. Okay. You say who and who are very similar, or who are in the same cluster. I can do it underneath. I can do it right way. Okay. So based on this, she actually worked out an algorithm. Okay. But the algorithm is a little involved on the mathematics. I probably just give you a little hand waving on the algorithm. The idea is this. Okay. You give me say what things I want to cluster, okay, and how many clusters I want to get. That means the K clusters. Give me a K, and then you give me some seeds. Say who and who are in the same cluster. Give me the seeds. Okay, you give me the candidate metapaths. I will work out the right combination of the weight of the metapaths. Okay. So let's look at her philosophy. I just do a little hand waving. If you like the mathematics part, which is a generative model, then you can read more. But I give you hand waving. If you do not understand it, if you're afraid, it's not I will not give the formula as part of the test. Okay, I just test the ideas. She basically partitioned this into 3 major steps. Okay. One called modeling the relationship generation. The general philosophy is, if you give me the cluster, give me the result, say this one should be a cluster, these 2 should be in the same cluster. You give me this, I will try to see underneath there must be some metapath, some different weights. Okay, make this cluster generated. Okay, simply says the cluster I give you is not a random. There must be underneath a model which can generate this one. Okay, so that means she will try to find some good likelihood this observation can be generated. Okay, and the generation essentially is based on the metapath, based on the likelihood, and based on the user guidance. Okay, the guidance essentially is you can tune your parameters, but to the extent you tune the parameter, the chance to generate the user-given clusters is the highest probability. That simply says, if you tune the metapath in these different weights, the example you give me, they really generated in a high probability. Okay, so that's the philosophy she work out, just to say how to weight different combination of metapaths. Finally, I can generate things you said that these should be in the same cluster. Okay, that means the user give examples. I give you underneath the engine to match your example. Okay. But this one is a little more statistic based. I just give you a general philosophy. Okay. That means you would think everything is a multinomial distribution generated the thing. That means you assume what you observed is something underneath the generative mechanism, the probability generate this one. Okay, the probability generate this one essentially is you give me the different parameters and different conditions. I have a conditional probability, and I can turn this into a generated model which generate k clusters, and the chance to generate what you get is high. Okay. But the detail, I probably will not get into the very detail. You know, you try to use the Dirichlet distribution. I do not know how many people ever, actually, I think last month or so, we got another Stanford professor who came here. I think it was she was doing the Coursera. She's a Coursera CEO now, Daphne Kohler. She has a very famous video on there called probabilistic graphic models. Anybody, if you go down to Coursera, probably the first course, there are two leads. One is Andrew Ng, and he gave the course called machine learning. Okay, the other one is Daphne Kohler. She gave the course is probabilistic graphic models. Okay, these two are the model course by Coursera. If you go to Stanford site, you also can find it. And that's the one actually is all based on Daphne Kohler's probabilistic graphic model. But the one, if you did not take it, I will not require you, to master it, because her book is that thick and fill up with all the formulas you may or may not like to read. It's probably one of the most challenging course in machine learning. Okay, but it's a very nice generative model. But I will not give you the details. Essentially, is you use those parameters. You, according to the Dirichlet distribution, you can generate this probability, and you try to give the chance to generate the maximum chance to generate this distribution. Okay, so that's essentially you try to find this cluster parameter. That parameter actually guides you to get right weight of the metapaths. Okay, and the whole learning algorithm to learn this parameter is a little like EM, iterative algorithm. I saw there's one student put a post on Coursera say everything is EM, which is not right. Okay, the EM actually is good for clustering, for certain classification methods. But if you compute like a PageRank, it's not EM. It's just iterative computing the eigenvector. It is not EM algorithm. Okay, if you need more explanation, you can discuss with me. But there are some computation iterative. It's just the nature of computation, like an eigenvector computation, but it's not EM algorithm. Okay. But I would like to show you the results. The results is using the real data. You will really appreciate this result. Okay. One result is using DBRP in research publications. You probably already got a lot of exposure. But this one is using YERP data, the real YERP data. I believe everybody using YERP, right? If you go to a new place, you try to find a restaurant or find a hotel, maybe you want to see how they judge those business. Then you try to find a good one, right? So the YERP data essentially is you got business, okay? You got a user who uses business, like you go to this restaurant or you stay several nights in that hotel. You may like to write a review. Okay? The review may contain certain terms, okay? Certain things you really like, you say, it's great, or you really hate it, you may say some nasty words, right? But anyway, you have a review, you have a ranking, you have terms, you have business like this. This is the heterogeneous network schema, okay? or you can think of this one from the MetaPath for Europe. Okay. And what she wants to see is she put two candidate MetaPaths. Okay. One called BRURB, another one is called BRTRB. Okay. What is BRURB? This B is business, R is review. Okay. This U is user. You can see this U is user. The other one, the middle one, T means term. Okay. And actually, these two MetaPaths, she wants to see what are the interesting things, okay, and which may determine how to do clusters on those business. Okay. And she used one is restaurant, say try to find 6 clusters, okay, and using her method comparing with other method, you probably can see her method using her method called path selection clustering. That means you automatically select the weighted paths, okay, the path selection clustering. And the other one, there are lots of other ones that were not introduced, is previous studies on clustering the business for Europe or for others. And you probably can see her method, no matter on the accuracy or on the NMI, this is normalized mutual information. It's another measure I did not introduce in detail, but later if we need, I can give you more introduction. I think I introduced this one in the previous, like a rank class algorithm, but did not. This is just another statistical measure. You can think this. You probably can see for both measure on all these different samples, 1% sample to 5% sample, this quality got far higher than any other methods. Right? So it simply says, using weighted MetaPaths, you can do a lot of very good clustering for business. Okay? But a very interesting thing is the selection of the MetaPaths, the weight of the MetaPaths, for different business, okay, they change dramatically. Okay? And she actually analyzed Europe. One is for restaurants. One is for shopping, okay, and she found that these for the user one, the MetaPath, actually the weight changes dramatically. Anybody can interpret this, like when you try to cluster shopping and cluster restaurants, why the user group will play so different role. Anybody can interpret this. Think about, suppose you go shopping, you buy clothes, okay? Or you go to restaurants. In shopping, you buy clothes. Not only you go to Macy's, you really buy in Macy's. That's where we're put in, okay? You just go to Macy's, just watch. It will not count. These are our transactions, right? You have a transaction, you have a review on the business, right? So why they are different? Actually, you probably can think about this. The shops, actually some shops are very expensive. Some shops are reasonably cheap. The users really can be grouped by the shops. You think about this. If you want to buy $200 a shirt, you probably belong to those very rich people. You will not go down to the very cheap clothes to buy only $3 a shirt. Okay, so you actually, your transaction, your business, your review actually will go down to the very expensive stores. Okay, but on the other hand, those people who buy like $5 a shirt, they will not go down to there to spend $20 to get a shirt. Right? So the user for the shopping, they really partition into different groups in a very clear way. But the restaurant is different. Why? Because you are not fixed to only go to one restaurant. Okay? You actually, sometimes, like Bill Clinton, he was a president, he went to McDonald's to get a hamburger, right? So that means no matter how much money you have, you may also shopping or get a restaurant, like a McDonald's, you can eat something. Okay? So people try different flavors, you can hardly group them just by the user groups, because the restaurant, you get some celebration, you go to an expensive restaurant. So that's the reason, and she actually found these meta paths, you try to group restaurants, group business. Actually, some based on like users may find a very good cluster, but some you may need other things like terms to group them. If you like the restaurant, maybe you get some terms, maybe weights more rather than users. Right? So you can see, for different things, you need a different meta paths to do clustering. Okay? So that's a very interesting observation. Okay? So we finished this clustering. Okay, you see clustering using meta paths using similarity is very useful. Okay, so this one, you guess what it is? This one I also took in Oslo. Norwegian in the past, that part got lots of Vikings, right? The Viking, they on the ship on the ocean, they can rob some other ships. This one actually is a big ancient time, the big Viking ship. Okay, so they actually found it in the ocean. They actually got it back. So this is the original Viking ship. It's very big. You can see the whole museum actually. The architecture is built based on the shape of the boat, because the boat, some part is very tall, very high. Okay, they just preserve the original one. Now we got into another interesting theme is classification. Okay, remember, for data mining, similar search is one, but clustering is important, but the classification is also very important. Classification, the general philosophy is, of course, you can do clustering without any label, but sometimes people do give you some good labels. Okay, you may want to use this label to find a good model, then later similar things can be predicted. Okay, so, but the heterogeneous network to do classification is a new thing. Okay, you think about this. The heterogeneous network, what are the new things? The interesting thing is all those objects, even they are of different types, they link together. Just to give you the research network, these are the conferences, these are the papers, these are the authors, these are the terms. Those are different type of objects, but they link together. You use this term, write this paper, publish in this conference, they're all linked. Then you give label on one thing. For example, you give label on paper. Actually, you will get the similar label propagated to authors, to conferences, right? You can propagate. That means you don't have to give everybody label. You give label to this type, you can propagate to the other types. And also, you give this type, they are linked. Your propagation, your judgment is based on the network links. So that's also different, based on these heterogeneous network links. And that's one. I got another student, Ming Ji. She also graduated. She's in Google now. And she got a very nice paper on how to do classification on these heterogeneous information networks. Let's look at this, how she did it. Okay. The interesting thing is this. Okay. The first thing is knowledge, the labeled knowledge. That means you give label to certain objects. These knowledge can be propagated through the multi-typed objects across this whole network. That's the thing you can rely on. That's a different thing from the homogeneous networks. Homogeneous network, you think you get a label, you propagate down to this author, the author propagate to co-authors. This is the propagation. Actually, this heterogeneous network is you give author can propagate a paper. Paper can propagate to the terms or to the venues. Then they propagate down to the others. Okay, so that's a different kind of propagation. And once they propagate, they start competing. You can think about this picture actually saying this. Suppose I mark this author as data mining author. I mark this paper as a database paper. Now you can see the database and data mining, they start propagating. Down here for this paper, they start competing. Okay, you can see some people say drag this one, say this one actually should belong to data mining. Okay, why? Because you can see this author is a data mining author, got this paper. This paper contains the term shared by this one, and contain a co-author also shared by this paper. But the other guy may say, oh, this paper actually propagate term. This is a database paper, propagating term this one, because they share common terms. So you probably can see you have multiple ways to propagate. Finally, they have to compete. Okay, so that's a way you get statistics. You can compete. You finally can judge what the label of this one should be. Okay. Now she got two very good papers. One paper actually called GNetMine. G means graph. Okay, it's a graph regularization based on network mining. Okay, the general philosophy is knowledge or label can be propagated. The information propagated is from the label objects via those heterogeneous links. You propagate onto the other objects. Okay, then the whole thing is a heterogeneous graph. Using some kind of regularization, you can propagate them in the right one. Okay, I will give you the formula, but this formula probably I will not spend too much time to interpret this formula. The general philosophy is this. Okay, if you want to judge certain thing with certain label, there's an objective function. That means there is a function to determine whether this label, this paper should be a database paper, a data mining paper, an AI paper. Okay, and how to judge this is based on their nearby, their linked objects, their similarity. That means you have two rivals, they're competing on this. Okay, see how similar, which one is more similar, you will propagate knowledge more down towards you. Okay, so what the general philosophy is, you got these propagation one, and you got some smooth constraints. This simply says you will do some kind of a smoothing and a regularization, so you may make this propagation somehow a little less, influenced by noise. Okay, but I will not give you the detailed thing. The general idea is just knowledge propagation. Okay, but I will give you her second paper, which actually is very interesting. I just give you a little philosophy you probably can see. The first paper published in the ECML PKDD in Europe. The second paper just a year later published in the KDD conference called rank class. Okay. The general philosophy is ranking-based classification. The philosophy is the propagation is not equal. Not every object you treat them the same. You try to find who plays more role, which object plays more role, you give them more weight in the knowledge propagation. And finally, you will be able to get a very good classification. Okay. So in the next lecture, I'm going to discuss this rank class algorithm. Okay, thank you.